Hello, everyone, and welcome to the Alan I. Carswell Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Sunna. I'll be one of your hosts this evening. I'm joined by Matt, Obada, and Shannon, and we have a wonderful presentation on the mysterious dark matter and dark energy. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada, and we broadcast every Wednesday night at 7:30 p.m. local Toronto time here on YouTube. For any questions or comments you have on our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. And if you have any questions about tonight's show, put them in the chat and we'll answer them live. You can always connect with us on Twitter or Instagram with the handle @York Observatory and Facebook at Alan I. Carswell Obs. Before we get started with our main show, we want to give you a little update on what you can see this coming week. First up, we have the planet Mars that is still shining bright in the sky, rising in the southeastern sky and visible all night long. There are also the gas giants Jupiter and Saturn that appear to be traveling through the night sky together and set in the southwest at around 8 p.m. this week. All three planets are easily visible with the naked eye, so no telescope required. However, using even a small telescope will reveal some surface details on Mars, Saturn's rings, and storms on Jupiter, as well as its 4 Galilean moons. Another object visible around sunset is the moon, which is currently entering its waxing crescent phase. The moon will be setting along with Jupiter and Saturn this week and will be very close to them in the sky, particularly tomorrow on November 19th, when it will lie just a few degrees away from each of the planets at sunset. Again, no telescope needed to observe this, but a telescope or even binoculars will reveal lots of craters and other details on the lunar surface. Now, if you're willing to stay up a little bit later in the night, you can actually catch the Leonid meteor shower that peaked last night and early this morning, but you can still catch it in the next couple days. These meteors originate from the comet Tempel-Tuttle and will appear to come from the constellation Leo at a rate of about 15 meteors per hour. They are best observed at around midnight when the sky is darkest, and all you need to do to see it is get as far away from light pollution as you can and look up. Finally, the International Space Station will be passing overhead tomorrow morning at around 4:30 a.m. if you're in Toronto. The ISS, which has 4 new crew members after the launch of SpaceX's Crew 1 capsule on Sunday, will initially appear in the southwest sky and will look like a bright star that is moving quickly with its path shown on the left of the slide. While you're out there, you will also be able to see the planet Venus rising in the eastern sky. So with that, we'll now start our main show. Take it away, Shannon.
Thank you, Sunna, for that amazing introduction. Good evening, everyone. I'm Shannon, and I'm here with Obada, Matt, and Sunna. And we're here from the Alan I. Carswell Observatory at York University. Tonight, we've got a great presentation about dark energy and matter. The universe is a very vast space of unknown. Our solar system is merely a speck in comparison to the universe. For centuries, scientists and theorists have tried to discover truly how the universe came to be and its composition. As you may know, the universe is made up of matter. Baryonic matter is the matter we interact with on a daily basis, and it's made up of atoms and molecules, which are made up of protons, electrons, and neutrons. For the longest time, scientists and astronomers alike believed that the entire universe was composed of baryonic matter, made up of materials we know. However, scientists were able to discover that the universe is not entirely made of baryonic matter. The universe is actually made up of dark matter as well. It's interesting that we can see and work with only makes up a small percentage of the universe. Due to this fact, there will always be continued research and interest with hopes that one day we may be able to actually understand the universe. Atoms only make up a small percentage of the composition of the universe. Atoms make up only approximately 5% of the universe. Wow, the number is much smaller than we expected, because this means that 95% of the universe has actually never been worked with by humans. So what else makes up the universe if we only know 5% of it directly? Well, as Matt and Obada will later explain, the rest of the universe is made up of dark matter and dark energy. Dark matter makes up approximately 27% of the universe. Dark matter is made up, most likely, of a few subatomic particles that have a weak interaction with matter. The more we learn about the universe, the more we learn about dark matter and dark energy. Some scientists began to notice that there existed objects which only emitted a little light or even no light, yet could still be recognized for its gravitational tug, such as stars and planets, which are bright objects. However, astronomers do not seem to know why dark matter seems to have a gravitational pull, but does not emit or absorb light. Dark energy makes up 68% of the universe. Einstein's general theory of relativity predicted that the universe was either expanding or contracting, but either way, the universe was not static. And at first, Einstein actually predicted that the universe was static. Even after all these years, many cosmologists want to understand dark energy on a more theoretical basis in order to understand and explain the rate of expansion. Some astronomers correlate the expansion of the universe with dark energy. Now, you may be wondering that yes, all of this is very much interesting, but what is it like to study such advanced and mysterious topics? Well, luckily today, we have a quote by Sophia Gad-Nasr, a PhD student studying cosmology and astroparticle theory. The universe is full of galaxies and stars, brilliant objects that form under gravity and make space-time a canvas of art. But the things we can see make up a mere 5% of what the universe is made of. The remaining 95% is invisible. Dark energy, a whopping 70% of the universe, stretches the universe apart faster and faster with time. And dark matter, the remaining 25%, is everywhere, and it holds galaxies together so they don't fly apart. It also doesn't interact with the stuff we're made of, so we can't see or feel it. We know the two share nothing other than the placeholder dark in their names. What they are, however, remain two of the biggest open questions in physics till this day. One way I'm trying to answer the dark matter question is by using simulations to test models that include dark forces to see how they reproduce our universe. Understanding its particle properties is crucial. They'll help tune experiments to look for dark matter in the right places. Thank you to our fellow student for highlighting the importance of cosmological research and giving us a recap on the universe. Now, Matt will be covering in more detail about the strange cosmological mystery of dark matter.
Well, thank you, Shannon, for that interesting introduction to the amazing topic that is dark matter. Baryonic matter was mentioned, as well as gravitational pull. So what is the difference between visible matter, we could say, and this mysterious dark matter? Well, we can start from the basics, as Shannon did, in order to explain this in an easier and understandable way. Dark matter is essentially, as its name basically tells us, something that is present in the universe, but we cannot see it. We can feel it, yes, but we cannot see it. How do we know that it's there? Well, as it was mentioned earlier on this presentation, only because of the gravitational interaction it has with visible matter, and also because of the relative absence of the mass in the momentum of galaxies. Scientists have calculated the mass of large objects in space by studying their motion, and at first it was expected to see material in the center moving faster than on the outer edges. But instead, they found the stars in both locations travel at the same velocity, indicating the galaxies contain more mass than what could be seen. Now, this relates to the topic that dark matter does not interact with electromagnetic force, ergo it does not emit or absorb light, making it, you guessed it, dark. Well, now it is hard to define dark matter because we don't even know what it is composed of. So we usually define it by comparing it with what we know and what we can see. Dark matter is really something that makes you curious about how the universe works like never before. Why? Well, because you have to take into account the fact that every star, planet, nebulae, gas clouds, galaxies, and all the visible matter is only 5% of what the universe has in reality. An outstanding 25% of the universe is made up of this dark matter, which we theorize it's not made up of baryonic matter because of its lack of absorption of radiation passing through it. Instead, we say that it is made up of other more exotic particles called WIMPs. Now, WIMPs. WIMPs stands for weakly interactive massive particles. Uh, they are the subatomic particles which are not made up of ordinary matter or baryonic matter, as we mentioned earlier. They are weakly interacting because they can pass through ordinary matter without any effects. They are massive in the sense of having mass, whether they are light or heavy, it depends on the particle. The prime candidates include neutrinos, axions, and neutralinos. Axions are particles which have been proposed to explain the absence of an electrical dipole moment for the neutron. Neutralinos are massive particles. There may be 30 times to 5,000 times the mass of the proton, but they are the lightest of the electrically neutral supersymmetric particles. Neutrinos are particles that don't make up regular matter. And we know that a river of neutrinos streams from the sun, but because they rarely interact with normal matter, they pass through the earth and its inhabitants. There are three known types of neutrinos. A fourth, the sterile neutrino, which is proposed as the dark matter candidate. The sterile neutrino would only interact with the regular matter through gravity, but all of this is so far purely hypothetical. The problem with this theory explaining the gravitational pull coming from nowhere is that the neutrino does not have enough mass to be a major component of dark matter, and observations have so far not detected any axions or neutralinos. Now, there is one last theory that seeks to explain this, but it also has some problems it cannot explain for the moment. It is the massive compact halo objects or machos. Machos are objects ranging in size from small stars to supermassive black holes. Machos are made of ordinary or baryonic matter, like protons, neutrons, and electrons, as we mentioned earlier. They may be black holes, neutron stars, or brown dwarfs. Astronomers have been detecting machos using their gravitational effects on the light from distant objects. When a massive object passes in front of a distant object like a galaxy, the light from the distant object is focused and the object appears brighter for a short time. Now, astronomers search for machos, which are usually brown dwarfs, in the halo of our galaxy by monitoring the brightness of stars near its center. It sounds like the obvious explanation, right? Well, the problem is that while faint machos have been observed, astronomers have found no evidence of a large enough population of brown dwarfs or machos that would account for all the dark matter in our galaxy. And well, all of this is meant to be the explanation for that 25% of the universe. But what about the rest of it? Obada will help us on that matter.
Thank you, Matt. Now I'll be covering the remaining 68% of the universe by talking briefly about dark energy and its discovery. Dark energy is a quite recent discovery. It was initially speculated by Einstein in the early 20th century. The idea was first sparked in the cosmological constant in Einstein's field equation. The Einstein field equation describes gravity as a result of space-time being curved, and is a way to describe space and the matter within it. The constant was essentially a way to balance out the gravitational forces of the universe, so that there is a counteracting force preventing a changing universe. Einstein seeked a static and unchanged universe, but later realized that any sort of local imbalance will drive the equilibrium one way or another. It wasn't until Edwin Hubble's observations in 1929 that showed solid evidence of our expanding universe. Einstein later admitted his mistake and called it his greatest blunder. Many of you are probably familiar with the Doppler effect, which was discovered by Christian Doppler in 1842. The theory initially applied to sound waves and said that when a sound source is moving away from an observer, the frequency drops. And when a sound source is moving toward the observer, the frequency is increasing relative to that observer. Now, if you listen carefully, this can be easily noticed by passing fire truck or ambulance. The theory is a fundamental property of all waves. Now, light, in some cases, behaves as a wave. In the case of light waves, a blue shifted, higher frequency light wave moving toward an observer, and a redshifted lower frequency light wave is moving away from an observer. This property can be observed for celestial objects, such as distant galaxies and star systems. This is exactly what Edwin Hubble decided to look for in the late 1920s. He studied the behavior of distant galaxies and found that they are redshifted and moving away from us. More specifically, he found that galaxies further away from our home galaxy, the Milky Way, are moving faster, and nearby galaxies are moving slower. This exact number for the speed is 74 kilometers per second per megaparsec. This means that for each megaparsec, which is a distance of about 3 million light years, a galaxy or a distant object is moving away from us, away from the observer, at an additional 74 kilometers per second. As an example, a galaxy 1 megaparsec away is moving away from us at 74 kilometers per second. And a galaxy 2 megaparsecs away is moving away from us at double that speed, which is 148 kilometers per second, and so on. In short, the further away a galaxy is from the Milky Way, the faster it is moving away from us, showing us that the expansion of the universe is accelerating. To drive the expansion of the universe, there needs to be a force opposite to gravity, which is where the concept of dark energy arises. Dark energy is mysterious, and its source is unknown, hence the name dark. The concept is much more theoretical than dark matter, and many aspects of it remain unknown. It's almost evenly distributed, causing the same expansion in every part of the universe. But what exactly is dark energy? There's more unknown than known about it. We know that it makes up at least 68% of the total matter of the universe, and we know that understanding it is a crucial part to our understanding of the universe. It can be observed directly. It doesn't interact with regular matter or any form of electromagnetic radiation. The only way we know it exists is by noticing its effect on surrounding galaxies. Many scientists speculate that it's a property of space itself. It isn't anything like regular matter. It can't form planets, stars, or galaxies. For now, the best explanation we know is that it's the energy driving space itself to expand. Next up, Sunna will outline some of the key research being performed to deepen our understanding of the subject.
Thanks, Obada. Now that you know what dark matter and energy are, you might be wondering how astronomers know all this and how new discoveries are made. There are several ways to study dark matter and energy that include studying the universe on its largest and smallest scales. One of the most reliable ways to study dark matter and dark energy is by using the cosmic microwave background, or CMB for short. The CMB is described as the afterglow of the Big Bang, which is the birth of the universe. This is the oldest light in the universe, and studying it can reveal many things about the universe, including what fractions of baryonic matter, and dark energy there are. Two important observations of the CMB came from NASA's WMAP satellite and the European Space Agency's Planck satellite. WMAP performed its measurements starting in 2001, and then Planck later in 2009, with Planck confirming WMAP's measurements. How do scientists use the CMB to study the composition of the universe? Well, to study dark matter, they look at the small-scale variations in the CMB, which indicate the density of matter in the early universe. By observing this pattern, astronomers can figure out how much baryonic and dark matter there is, since only a certain amount of each will reproduce the pattern observed. To study dark energy, scientists look at the shape of the universe, which can also be determined by studying the CMB. Both the WMAP and Planck satellites indicate that the universe is flat, with a curvature of only 0.4%, and this small curvature requires a large amount of dark energy. If you want to learn more about the CMB, visit our YouTube channel to see last week's TeleTube that aired on November 11th, all about the CMB. Another way to study dark matter and energy is by observing the structure of the universe by taking sky surveys with large telescopes. One example is the Dark Energy Survey, which creates large-scale maps of galaxies and baryonic matter. Scientists will use these maps to study the expansion of the universe, both currently and over its 14 billion year history, to learn about dark energy. Dark matter can also be studied by observing galaxies and galaxy clusters, which are massive collections of galaxies. Both of them contain large amounts of dark matter that have a massive influence on their dynamics, so scientists can learn more about dark matter by studying them. One interesting example is shown on the screen, a galaxy called NGC 1052-DF2, which has no dark matter. While many studies aim to learn about the properties of dark matter and dark energy, scientists will also need to detect the actual particles associated with them, such as WIMPs that Matt mentioned earlier. And to do this, they need to use particle physics experiments. There are many experiments that are trying to detect dark matter from the cosmos, which can be done by observing it colliding or interacting with a material here on Earth. An example of this is SNOLAB, which is in Sudbury, Ontario. Their experiment, DEEP, which is shown on the slide, is the largest dark matter detector of its kind and detects dark matter particles directly when those particles interact with argon in the detector. Particle accelerators can also be used to create dark matter particles during collisions and then detect them afterwards. One of these particle accelerators is CERN's Large Hadron Collider, or the LHC, located in Geneva, Switzerland. The LHC collides protons that are traveling at close to the speed of light, and when they collide, they produce new particles. Scientists are on the lookout to detect any dark matter particles that are produced in these collisions and would be detected indirectly. Finally, a lot of important research is performed by using simulations, where scientists input the laws of physics into a computer and then trace the motion of dark matter particles over time. These results of the simulations are then compared to what is observed in large-scale observations of the universe. Just one of the many simulations created is the Millennium simulation, and a visualization of it is playing on the slide. The Millennium simulation is one of the largest simulations ever created and tracks 10 billion particles enclosed in a cube of a volume of 8 billion light years. The video shows the dark matter structure of the universe and zooms in on a massive galaxy cluster. You can see the structure of dark matter in the simulation, with some densely packed regions and some regions with almost nothing in it. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Shannon, Matt, Obada, and myself, Sunna. Make sure to leave any comments or questions in the comments section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, please see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.